All right, thanks for coming back. So next lecture is by Professor Manikandan Mathur from IIT Madras. He's going to talk about internal gravity waves in the ocean. Mani is experienced with lab experiments and cruises in the ocean. So he has a lot of information on these different kinds of waves in the ocean. So he's going to talk about all the spectrum of waves with focus on internal gravity waves. Thanks.
Thank you, Jim. So, good morning, everyone. Thanks again to Jim and the other organizers for giving me this opportunity. So I have planned a pedagogical lecture on internal gravity waves with all the applications focused on the ocean. Some of these ideas are relevant for the atmosphere as well, but I'm not an expert on the atmosphere. But we can talk about it offline or after the talk if you are interested in the atmospheric application of some of these ideas. And several of these ideas are relevant for modeling waves in general, both in the atmosphere and the ocean. So while I will focus almost entirely on internal gravity waves, these would extend to other systems as well, which can support waves. And finally, time permitting, I would like to present a little bit on something outside of internal gravity waves too. That's what I have listed out here as Rossby waves. All the content here is thanks to Nihar Paul, who's a postdoc in my lab. He's also present here in the audience. Okay, so this is the overview. Thanks to Jim for that fantastic introduction on geophysical flows. So I take off from where he landed. It's very convenient to have that background. So ocean in general is a very large system, right? And not only is it very large, it's also quite difficult to access in terms of making scientific measurements. So in that sense, oceanography is relatively a new field. People have been trying to make measurements for maybe close to a century now, but it's still nascent in terms of how much of the ocean we can cover in terms of measurements. And a lot of what we know about the ocean has been driven by what we have seen in measurements. It's not all modeling all the time. Yeah, you do try to build models, but based on what you see or based on trying to understand what you see in observations. So one such way is, of course, the obvious way is to go in a ship, carry some instruments with you and see what measurements you can make in the ocean. But another very useful way of making measurements in the ocean is to attach your instruments to what is called a mooring. Leave it there at a specific location in the ocean, let it make measurements all through the year. And then after a year, you retrieve the data and you learn a lot more than how much you can learn, let's say, based on a week or two long cruises. There are pros and cons for all these approaches, but what I'm going to present here is some data from such a year-long mooring measurement. So what multiple oceanographers around the world have done is to deploy these moorings at various locations based on different motivations. And one of these plots is what Jim showed in his presentation. This is from the review paper by Ferrari and Wunsch, mainly focused on what drives the various dynamical processes in the ocean. So what they've done here is to have left an instrument which has current meters at multiple depths going from the surface of the ocean all the way to the bottom. Of course, the resolution of the vertical resolution of the data would depend on where all the dynamics happen. So it will be more highly resolved close to the ocean surface, not so resolved closer to the ocean bottom and so on. And you've collected this data year long, right? And then you try and see what the frequency content in the kinetic energy is. So on each of these plots, on the y-axis is the power in the kinetic energy. I think it's the power spectrum in the kinetic energy. So U square plus V square. These current meters are able to measure only the horizontal currents. And on the x-axis is a frequency. In oceanography, it's common to express it in terms of cycles per hour. So just to give you a perspective of what these numbers mean, the number you see here is 10 power minus 3 cycles per hour. So that would be around 1,000 hours for one cycle. 1,000 hours is around 40 days, right? So you're talking about a 40-day time period for a value that's close to 10 power minus 3. And if you come to 10 power 0, so that's one cycle per hour. That's much faster than a day's time scale. So 0.1 is where you will be more or less close to a day's time period. And these three different plots are from three different depths. I believe this is the shallowest depth, or it's at a depth that's close to the ocean surface. Just to make sure I'm not wrong, I included the caption from the paper as well. So that says 128-meter depth for the uppermost plot, then 1.5 kilometers and 3.9 kilometers. So for those of you who are new to the field, it's also quite, the first time I learned that average ocean depth is around 4 kilometers. That was quite impressive for me to hear, right? And what you see here is all these plots. First, there is a clear peak. That's what I've pointed out here. No, that's in the second point. So let's talk about this part of the spectrum. That's in the low spectrum, low frequency range. So that's around 40 days or larger time scales. And it seems to be more or less flat here. And this is what is known as the geostrophic eddy range. And the dynamics in this range is largely driven by what Jim presented as geostrophic or quasi-geostrophic dynamics. And then come to the right, you see this peak that is present at all three different depths. And the peak occurs at a frequency, this is referred to as the inertial frequency here. In a couple of slides, we will see how it is related to the Earth's background rotation. It goes as the frequency F goes as 2 omega sine theta, where omega is Earth's background rotation and theta is the latitude you are at. Okay, and so that's a clear peak that you see, and that seems to be separating this regime where the curve is more or less flat and this high frequency wavy regime. I am no expert in explaining these slopes, but of course you do notice that there are different slopes for these different frequency regimes. And we are going to be thinking entirely about this high frequency range in the rest of this talk. Right? And you also see another, so this is a strong peak and it's also seems to be wider than the other peaks that are present in the system. The second peak you see here is at what is called the semi-diurnal frequency. So this is roughly half a day, exactly half of the lunar day, but close to half of Earth's day. Okay, and that is related to the dominant frequency that is present in the tides caused by this Earth-Moon gravitational system. Of course, we don't know anything about the spatial structure of these signals. Right now, it's just at a single location in the ocean, and I see that these frequencies are present. There are occasions when there are frequencies are present at other locations as well. In fact, here they have pointed out there is a tiny peak that is present at 2 times M2. M2 is the semi-diurnal frequency. So there are these higher harmonics that are present as well. Whether are they generated by some nonlinear processes of these primary harmonics, or is there a generation mechanism that's directly putting energy into 2M2? We don't know all that right now. And we try and understand some of these processes when we build models to explain these observations. And here you also see what are called O1 and K1. These are related to the other tidal constituents, including the tide associated with Earth and Sun, right? And at this specific latitude, it turns out the inertial frequency and this O1, K1 frequencies are quite close to each other. And it turns out that's also interesting. So some latitudes could be more dynamically active in terms of these waves than others, depending on how close these diurnal frequencies are to the local inertial frequency. What you also notice is, as you go to deeper parts of the ocean, there seems to be significant strength present in the M2 tides, right? But the relative contribution or the amount of energy that is present in the at the inertial frequency seems to substantially reduce. If we can read these numbers, this is around 47% of all the energy that is present in the high frequency range. That comes down to around 18% if you go close to the ocean bottom. But the M2 tide seems to be active throughout the depth of the ocean. And the frequency range between F, we have talked about it quite a bit now, and the Brunt-Väisälä frequency. Again, this goes back to Jim's talk. He was talking about a natural frequency that a fluid particle would go into in a stratified system, right? And that's your Brunt-Väisälä frequency. We will talk more about it. That is the frequency range over which waves can propagate in these stratified, rotating stratified systems. And so that's dominated by the internal gravity wave dynamics, which is what we're going to talk about. One of his slides said F less than omega less than N. That's exactly this. And there are also signals present at frequencies much larger than N. This corresponds to small scale turbulence. Okay. But here in these plots, this is also cut off here. This is owing to the limitation on how often you are able to collect data. These instruments collect data roughly once an hour, because these have to collect data for the entire year. You need enough battery and so on. So you are limited in that sense about how often you can collect data. Now, these are two other plots from very different latitudes. This is at a lower latitude compared to what I showed in the previous slide. So you see that the inertial frequency value itself has shifted to the left. Because lower latitude 2 omega sine theta, theta is smaller. So the corresponding Coriolis frequency is also inertial frequency or Coriolis frequency. I'll use it interchangeably. But this O1 K1 is still, now it's larger than the inertial frequency. There isn't such a prominent peak at these diurnal frequencies. The semi-diurnal frequency and the higher harmonic, the first higher harmonic also still seems to be present even at this very different latitude. And just to highlight that this is not specific to the northern hemisphere, there is some data here from the southern hemisphere too. But interestingly, now at a very large latitude, this is 50.7 degrees south, where now the diurnal frequency is even smaller than the Coriolis frequency, and you still see these two peaks. And it's also noticeable that the Coriolis inertial frequency peak seems to be always much wider than the peak that you observe at the semi-diurnal frequency. So in some sense, let's keep in mind that you have these waves have a range of frequencies around the inertial frequency. So it's not always exactly at the inertial frequency, whereas the semi-diurnal activity seems to be a little more focused at the M2 value. This is all I wanted to say about these spectra. Again, resolving spatial scales is a much more challenging job. These days, it's done reasonably well by satellite measurements. They resolve scales of around, let's say, 50 to 100 kilometers, not a bad job by satellite measurements. But again, satellite measurements look at only the surface of the ocean. So they don't give us information about what happens in the subsurface. These kind of instruments give useful picture on what the vertical structure looks like if you have sufficient number of instruments or sufficient vertical resolution, but there is no coverage in the lateral direction. So oceanography is about nicely combining these kind of measurements with satellite data and ship-based measurements, which can make measurements at very fine temporal scales, and see if you can build one unifying picture combining all these data, which all have their own advantages. All right, so what now distinguishes these geophysical flows from conventional fluid mechanics, which I believe most of you have seen in some part of your education. Right, one is the effects of Earth's background rotation. Again, thanks to Jim for covering that aspect quite well. So I'll rush through this slide. I just want to highlight that at any given latitude, it's the component of Earth's rotation in a local normal direction, which I call here as omega z, that seems to be more dynamically relevant or dynamically more relevant than the component of Earth's rotation in the tangent plane. Okay, there are also a group of researchers who work on what are those tiny effects associated with omega y, and they try to highlight where there are regimes where that effect is actually not negligible. But we forget about omega y for the rest of this lecture. Omega z is the only dynamically relevant component of Earth's background rotation, and that goes as twice. That again comes from the Coriolis term. If you write down the equations of motion in the rotating frame, that is written as twice Earth's 2 times omega z, and omega z itself is omega resolved in this direction, which turns out to be sine phi. And if you want to do a expansion or account for the fact that this component is changing with latitude, you write it as 2 omega sine phi phi associated with the central point at the location where you're working at, and then account for the fact that it's also having some variation in the meridional direction. So the direction that where you increase or decrease in latitude is referred to as a meridional direction, and that gives you the beta plane approximation. I'm going to spend the next few slides keeping only F naught. In fact, no, I am going to spend the next few slides keeping only the stratification, not worrying about F naught and beta. Then I'll add F naught, and then I'll try and see what adding beta also does to all this wave dynamics. All right, so the second outstanding feature of these geophysical flows is the effects of stratification. That's not too common in conventional fluid mechanics we study. What do we mean by stratification? The ocean is stratified in the depth, along the depth direction, the Z direction, in both temperature and salinity. And depending on which part of the ocean you are in, one of the two is the more dynamically more important species. And in fact, in the same part of the ocean also, depending on which season you are at, it could be either temperature or salinity that determines what is contributing to density changes. And a very, very idealized model of the ocean stratification is that you have upper few tens of meters. Again, that depth can vary, where the density is more or less uniform because this is very active 3D turbulence driven mostly by the wind forcing that acts on the ocean surface. So you have what is called the mixed layer at the top, and then you will have very strong density changes right below the mixed layer, and that constitutes what is called the pycnocline. Okay, and then the deep ocean is modeled more or less as a uniformly stratified flow, which corresponds to n being constant. So the Brent-Weisel frequency here is proportional to the density gradient. So constant density gradient is the deep ocean, very strong variations in the density gradient in the pycnocline, and the uniform density. So n is going to be equal to 0 in the mixed layer. And there are very interesting phenomena that can happen when these waves are encountering this kind of a background. And we will see what they are as we go along, at least some of those processes. Okay, so that finishes my motivation or background on geophysical flows or on the ocean specifically. And we'll talk a little bit about what internal waves are. So as again, Jim has brought this out quite nicely. You consider a stratified system. The color here indicates density. So let's say you set up a system in which density is heavier at the bottom, lighter at the top. So this is naturally stable. We all know heavier fluid sits stably below lighter fluids. And we are talking about if you give a perturbation, it's not going to grow. It's a stable system. But then how exactly that perturbation is going to propagate in this system? If you take a fluid parcel, Jim pointed this out quite nicely again. You displace that fluid parcel, it's going to get into some oscillation, simple harmonic motion, and that natural frequency is what is called the Brent-Weisel frequency, and that depends entirely on the density gradient. Okay, these two are G and rho naught are constants, so n is directly proportional to the square root of the density gradient that you've set up. So you can do the classical small perturbation or linear stability calculation on such a background where there is no flow, there is just a uniform, stably stratified fluid. You can consider small two-dimensional perturbations and derive the equations that govern these small two-dimensional perturbations. This equation, W is the vertical velocity perturbation, capital N I've already pointed out as the Brent-Weisel frequency, and this is what constitutes your internal wave equation. Background rotation has been completely ignored at this stage. And you do the classical thing in wave mechanics, which is to look for plane wave solutions. So you assume an exponential dependence in all directions that are homogeneous. And in this problem, both x and z are homogeneous directions because there are no variations in the background along x and z. N is constant. And in the x direction, there are no variations. And you look for exponential dependence in time as well. And when you look for these plane wave solutions and substitute in your governing wave equations, here I have assumed the perturbations are of small amplitude. So when you substitute these plane wave solutions, you get a relation between the frequency omega and the spatial wave numbers kx and kz. This is what constitutes the dispersion relation for internal waves, right? And that turns out to be in this form, omega square equals n square sine square theta, where theta here is the orientation of the wave vector that you're considering. The wave vector has horizontal component kx and the vertical component kz. So the orientation of the wave vector with the vertical, which is the gravity direction. Right? And that's what is indicated here. You can also rewrite, if you want to write this cot square theta, instead of writing it in this form, it's also possible to directly write down cot. This is just a restatement of this equation. This is what your dispersion relation is. And it turns out it contains many interesting properties that makes internal waves worthwhile to study even if you don't care about the ocean. Okay, so this is why a lot of physicists have gotten involved in research on internal gravity waves. Okay, first, given a specific frequency omega that is typically set by what is the forcing mechanism, there may be some frequency like the tides. So there is a frequency that is present in the forcing itself, and a linear response would give waves at the same frequency. So given a frequency omega and a strength of a background density gradient, which is specified by n, the dispersion relation does not tell you what the specific kx and kz should be. It just tells you what the orientation of the wave vector should be. It only specifies theta for me. It doesn't tell me what kx and there are multiple combinations of kx and kz that will give me the same theta. And that itself is fascinating. Then one wonders, okay, given a frequency, what determines the wavelengths of these waves that are generated? Second, as theta goes from, as the frequency goes from 0 to n, capital N, the theta here goes from 0 to pi by 2. All right. So the only range of frequencies that are propagating are going from 0. Please remember, there is no background rotation. My f is 0. So earlier I said the range of wave propagation is f to n, and f is 0. Now I am just saying it's 0 to n. So any frequency that is larger than n is going to be evanescent. It's not going to have this propagation property. It is going to have exponential decay from where it is generated. And finally, this is one of the most interesting aspects of this dispersion relation, which is that the phase velocity associated with these waves is orthogonal to the group velocity. What's the phase velocity? You sit on a peak on the wave, and let's say you want to continue to remain on the peak, you'll have to move with some velocity, right? And that's a standard concept across waves, acoustics or surface gravity waves, any waves you think of. So, and in 2 dimensions, it's going to be a vector. And that is the phase velocity, and group velocity is the velocity with which wave packets or energy propagates. And often the 2 velocities are not necessarily the same. That is already known from non-dispersive systems, dispersive systems. But in this specific case of internal gravity waves, not only are they different in magnitude, it turns out they are orthogonal to each other. And that's the first time you see it, it's a little stunning. So you have, in this picture, you have lines of constant phase given by this color, right? And you will see that in if I play a movie of this wave, you will see these lines of constant phase move along the direction indicated as phase, whereas the energy is propagating in this direction. Let's see that a little more clearly via 2 different experiments. Before that, given an omega and an n, this dispersion relation specifies 4 different possibilities for theta, given by these 4 different little schematics or depictions. Okay, so one of the first experiments on internal gravity waves in a lab was done in the 1960s, where a stratified system using salt was set up in the lab. Why did they use salt and not temperature? Salt is much more easier to control in a laboratory setting. Temperature is diffuses too fast, so very difficult to handle in lab setting. And if you're interested in how to set up the stratified system, I am happy to talk after the lecture. You take a cylinder that is present at the center of this picture, and you just oscillate the cylinder up and down. Okay, because the dispersion relation told me only the frequency at which I provide the forcing matters to determine in which direction the waves will propagate. So here it doesn't matter in which direction I oscillate the cylinder. It could be back and forth in the horizontal direction or back and forth in the vertical, but I specify the frequency omega at which it oscillates. All right, and it results in a picture like this, where like I showed in the previous slide, 4 possible solutions for theta given an omega and n, and you get what is called the St. Andrew's cross because of its resemblance to the cross. And the group velocity direction is indicated by these blue colored arrows, and the phase velocity is indicated by these yellow colored arrows, which is orthogonal to the group velocity. Then during my PhD, I built this wave generator because it is quite nice to see this generation mechanism. But in the ocean, the outstanding question is, once these are generated, how do they dissipate? Right? And in a laboratory experiment, you would like to have some control over the kind of internal waves you generate. And in this experiment, again, if you had this in a large tank, all these waves that you have generated will quickly reflect from the side boundaries. And then once you go sufficiently far from the cylinder, you will have a very complex wave field. But you would like to build a system in which, let's say I can generate only one of these 4 branches. That would be very convenient to have. Can I specify the wave number that is present in this internal wave field that I generate? That will also be, then I would be able to do focused studies on this specific frequency, this specific wave number, what are its, let's say, braking mechanisms. Well, ultimately, people are interested to know what kind of braking or what kind of mixing that these internal waves can ultimately cause in the ocean. So we built this wave generator. It is essentially a stack of oscillating plates. So each of these rectangles is an individual plate. All these plates can oscillate back and forth in the horizontal direction. So one thing we did was, by presenting a boundary like this, we completely eliminate the 2 branches that go to the left. So that's the first thing we did. Out of those 4 branches in the St. Andrews Cross, 2 of them have been eliminated just by presenting this boundary. And then how did I eliminate the upward going internal wave? We made sure the phase is propagating upwards in this wave generator. So that's how we carefully planned the movement of each of these plates. And then that would then choose only that branch of the solution that has an upward component for the phase velocity. Right, so if you recall from this picture here, so the one where that is propagating to the left has been eliminated. So let us look at the phase velocity. So the one has, let's say, that is propagating to the right, one has a downward component and the other has an upward component. And if I ensure that the phase velocity is strictly moving upwards on my wave generator on that boundary, then I eliminate the possibility of this fellow as well. Let me quickly show you a movie of this experiment. Okay, so this is what the raw movie looks like. You have seeded the fluid with glass particles, illuminating them with a laser light sheet. Let me play that again. And the raw movie itself does not tell you much. If you are trained to look very carefully, you can detect internal waves here, but otherwise all you see is some changes in the light intensity, some particles moving, right? And you process these images on loop. This is the last time anyway. There's not much to learn from here. But I'm just saying that there are internal waves present here and you'll have to trust me on that. But if I play this second movie, all right. So given that background on what characterizes oceanic flows, and then some introduction to internal gravity waves, let us now ask the question of why should internal waves be important to study in the ocean? I think I have sufficiently motivated that even from a basic physics viewpoint, it's an interesting system. But now let's see how they play a role in the ocean. So this is a statement from the review paper by Monk and Wunsch. Some of these views have evolved over the last couple of decades. I'm sure Bishak will have something to say later in the day about this. But let me anyway recall what Monk and Wunsch pointed out in the late 90s. Without deep mixing, the ocean would turn within a few thousand years into a stagnant pool of cold, salty water. Okay, so without any mixing, you are talking about fluids of different densities, and you're talking about irreversible mixing. You mix the two, it goes into some intermediate density, and then you cannot reverse it back or separate it into two fluids of separate densities. So such irreversible mixing, if it is not there in the deep ocean, not just on the ocean surface, then the claim is that the ocean would turn into a stagnant pool, which we know is not right. There are very strong circulations. Jim showed several movies that indicated that there are very strong currents present in the ocean, and that is not just present on the surface. It turns out there are very strong currents present in the deep ocean as well. So this stagnant pool is incorrect, and it's not just one single density cold salty water. It is always stratified both in temperature and salinity. So a lot of oceanographers thought about what could be drivers for this mixing in the deep ocean. Okay, and in this paper, they identified two different sources for mechanical sources for what can cause mixing in the deep ocean. One is the tides, which we have talked about already, and the other is the winds. That's intuitive because these are acting on the ocean surface all the time. So one should think about what's happening to the energy that these winds are putting into the ocean. This is a schematic of the large-scale circulation pattern in the ocean, where the blue color indicates that these are present at very deep parts of the ocean as well. Okay, and there are specific locations where there's also a large vertical transport when the fluid has to go from these currents that are present in the deep ocean to what is present on the surface. But those are topics for another day. So in the ocean, away from topography, the internal wave field is the only serious candidate that can cause this vertical mixing. So since this paper, there's huge interest in thinking about how much energy is actually being put into internal waves from these two different sources. That's the first question. And two, what are the mechanisms by which these internal waves will dissipate or finally cause mixing? And they may not even cause mixing locally at the location where they are generated. So you are interested in both these questions. How much energy is going into these internal waves and where exactly is it causing mixing? So we will focus a little bit on generation processes, a little bit on how they propagate and potential mechanisms that could lead to internal wave dissipation. All right. So for the first question, the first source was tides. So here is a plot based on a combination of satellite measurements and some ocean model. That is somewhat along the lines of what Jim showed. And you combine the two to estimate where, at what locations, or what is the strength of dissipation, irreversible conversion of tidal energy into fluid flow motions in the ocean. Right? Then this energy cannot be given back to the gravitational system between Earth and Moon. And the first thing you notice is that this tidal dissipation is quite strong at coastal locations. And there are also some deep ocean locations when this tidal dissipation is strong. It turns out they are quite close to regions where there are very tall topography or mountains that are present at the ocean floor. So the general understanding from this line of research was that regions of rough bathymetry or rough ocean floor or coastal regions are very strong locations where very strong tidal dissipation occurs. Then the next question, people and evidence suggests that 25 to 30% of this tidal energy dissipation is actually via conversion to internal gravity waves. That's a huge fraction. Right? These tides acting on the ocean floor, there can also be boundary layer dynamics, there can be dissipation associated with those boundary layer dynamics, but you're talking about a significant fraction is via generation of internal gravity waves. So when I talk about tidal dissipation here, I mean that it's irreversibly transferred from the tides into these fluid flow motions. So these energy put into the internal gravity waves ultimately has to contribute to mixing or get converted into heat. What time do we have? So 15 minutes. Okay. So then there is a huge body of research on how internal gravity waves, internal tides are generated. Internal tides are internal waves at the tidal frequency, and they looked at how they can be generated, particularly near topographic or bathymetry, rough bathymetry sites. And this bathymetry could either be continental shelves or small scale topography, but that are quite rough. And if you have such rough topography over sufficiently large scales, that could result in significant generation of internal tides as well. Or these isolated deep ocean topography that are quite tall. And the way you model them in laboratory experiments is you have this shelf-like topography or deep ocean ridge-like topographies. Instead of having a barotropic tide or the entire fluid column moving with respect to your bottom topography, you move the topography with respect to stationary fluid. That's for experimental convenience, and you see these internal gravity waves that are generated. I would say this generation process is to order 1 or order 0. I would say it's reasonably understood as to how different shapes have different efficiencies of internal tide generation and so on. The next question you ask is, once you have an estimate of how much energy is going into these internal tides, how can they finally dissipate or contribute to vertical mixing? I am in my research, or I think in the general community, is quite far from fully understanding that problem, but they do start identifying different mechanisms by which the energy in these internal tides could go into some other form that will ultimately lead to small scale turbulence and mixing. A couple of those mechanisms are scattering by the ocean environment that they encounter. And that ocean environment could be in terms of other topography that they encounter. So you have internal tides being generated at one location. As they propagate away, they encounter other topographies of different shapes. So how do they get scattered? Can energy be transferred to smaller scales that will ultimately lead to turbulence? Or there are other nonlinear processes like parametric subharmonic instability. That's a very specific term for the general class of triadic resonances that can occur. So this is quite efficient in transferring energy from the frequency at which you have forced these internal waves to other frequencies. If you remember from the spectrum, I showed that there seems to be some small peak present at 2 times M2. Perhaps such a mechanism is at play where the primary energy is being transferred to other frequencies. Then there is a whole body of research. Jim is an expert on this, on how these internal waves can interact with other background flows. So there are flows that are governed by the geostrophic dynamics, and that's happening at slow time scales. You're talking about these high frequency waves, but they are not separate or independent of each other. People are still trying to understand how much there is an interaction between these multiple time scales. And that is also one of the challenges of why you are unable to build models which take care of all these different dynamics quite easily, right? So then you try to build semi-analytical models or semi-numerical models. that takes care of interaction between these different time scales. Okay, so in the next couple of slides, I'll show you the scattering phenomenon, one by the non-uniformity in N. Right, so instead of uniform N being throughout the ocean, as I showed in one of the slides, there is a strong pycnocline and then there is also a mixed layer at the top. The mixed layer depth can vary depending on the location and season. So here is a basic physics-driven research that we did based on internal wave scattering by non-uniform stratification. We realized the problem is actually not too different from the interferometer in light, where if you encounter a sudden change in the stratification, so you have an incident, here is an incident light with, and it's encountering an interface across which the refractive index is suddenly changing. And if the background stratification, the density gradient suddenly changes, there is a similar interference phenomenon that happens where some wavelengths tend to pass through, right? And some wavelengths tend to get reflected. And in this specific piece of work, we established a one-to-one analogy between, but we also highlighted some differences between what happens in light, which is understood very well for centuries, and the equivalent phenomenon in internal waves. This is an example of internal tide scattering. Okay, so what I'm talking about here is some internal wave that's been generated far to the left from a remote location. That's, let's say, gone into the deep ocean, and as it propagates, it encounters other hills that it has to interact with, right? And the main governing parameter in this problem turns out to be the relative import, or how steep this topography is, that's quantified by the slope that you see here, relative to the slope of the internal wave. Internal wave slope is something we discussed during the dispersion relation discussion. So if the topographic slope is shallower than the internal wave slope, you refer to it as a subcritical topography. And if it is steeper than the internal wave ray slope, then it's a supercritical topography. It turns out if it's subcritical topography, all the incident energy actually gets through. But even while it is getting through, energy is getting transferred to smaller scales. On the left, you see energy primarily in mode 1. Mode 1 in the sense that this is the largest wavelength that can be accommodated in the ocean depth. But then you see the transmitted side, there seems to be length scales that are present that are smaller than the length scales in the incident mode 1. When you have a supercritical topography, the problem becomes even more interesting. Not only there is energy transferred to smaller length scales, which is one of the pathways towards instabilities and turbulence, you also have a significant amount of reflected waves. Because if there was no reflection, you would still see a clean mode 1 on the incident side, but then you have strong reflection as well from the supercritical topography. In the interest of time, I will not give you more details. I'm happy to discuss in the rest of the meeting if someone's interested. So the second part of the problem is asking the same questions of the energy being put into the ocean from the winds. Right? Like I said, the people studied how exactly internal tides can be generated from barotropic tidal forcing on topography. Now the question you ask is, how exactly can internal waves be generated from winds? It turns out winds, they don't have any frequency present in them as such. Right? What you see during storms is sudden changes in wind stress. That's like a delta function forcing. So you have, let's say, a calm environment and suddenly a storm arrives, and at that location you encounter a sudden change in the wind stress. And that sudden change in the wind stress can excite inertial motions in the mixed layer alone. That's a very simple model that you can build. So where you consider the mixed layer as a very thin slab of fluid, and you subject it to a sudden change in the wind stress on the surface. There are a lot of approximations going into this model, but you can show that inertial motions in this entire thin slab of fluid at or very close to the Coriolis frequency will be excited. So this is in this maps. Sorry, I did not tell you enough about these maps. This is similar to the other global map that I showed. Again, a combination of satellite measurements and some model that shows how much energy is being put into the ocean inertial motions from the wind. And you see that it is this energy input into inertial motions from the winds is intensified on western coasts, okay, and during winter storms. That's the essential message. And another important message from this piece of work is that the amount of energy input into these inertial waves like internal tides are internal waves at tidal frequency, inertial waves are internal waves at the inertial or the Coriolis frequency. And the energy input into these is comparable or sometimes even be larger than the energy put into internal tides. So in that sense, both tides and winds are quite important. So what do we do in the internal wave modeling community? You try and derive a similar dispersion relation now, including the background rotation. So in the next couple of slides, I'm going to include the background rotation, but I'm going to assume it's constant. It's just F equals F naught, no beta or no variation of the background rotation with latitude. When you do that, the dispersion relation gets modified in this manner, where earlier cot square theta was n square minus omega square by omega square. There's an additional F square term that comes in here. And for this term to be positive, you can show that now the range of frequencies which allow for internal wave propagation is now between F and N naught. But there is also another interesting regime, which is if the Coriolis frequency is larger than N naught, you have this range also that allows for internal wave propagation. Okay, this cannot happen if there is no background rotation. Right? If there is stratification and there is no background rotation, by definition N naught will be greater than F. So we are talking about this range. But if you are in regions where there is no stratification, or let's say you are in the limit of zero stratification, then all the frequencies from 0 to the local Coriolis frequencies will be propagating. And from the winds, you mainly generate these near inertial waves, and that corresponds to also a theta of 0. Theta refers to either the wave vector orientation with the vertical or the energy propagation direction with the horizontal. And I hope I have now convinced you that the two different mechanisms that contributed to the two main peaks that we saw in the spectrum. Alright, there is something about fluid particle trajectory. What do fluid particle trajectories look like in these internal wave fields? Let me not spend too much time, but just to highlight that individual fluid particles are actually oscillating about their original location. That's what is amazing about these waves. They are capable of transporting energy and momentum over thousands of kilometers, while individual particles are essentially just remaining at their original location. Okay, but you can still talk about higher order effects in maybe individual fluid particles could go a little bit away from where they were originally. So more importantly than mass transport, momentum and energy transport is what makes these wave systems quite interesting to study. Okay, and these near inertial waves from the winds can be understood from mooring measurements as well. Just to give you an idea, India, the Ministry of Earth Sciences of India maintains a very nice network of these moorings deployed at different locations in the Arabian Sea and the Bay of Bengal. Okay, you can get a lot of information from either the websites of INCOIS or NIOT. I'm happy to tell you more if you're interested. This is from one such example analysis done by PhD student Dipanjan at IISc, where you looked at the response of the ocean to a specific storm event and highlighted how, depending on what season you are at, the response of the ocean could be quite different. So in this specific example, you see that these near inertial waves that have been excited in the mixed layer, they seem to clearly propagate downwards if you are looking at it in the August month. This is all from the Bay of Bengal region. But a similar process, another storm arrives at a much later part of the season, sometime around end of September. Now the river waters have entered everywhere in the Bay of Bengal, and they result in very, very shallow mixed layers, right? And that means the downward propagation that you see very clearly here is not so clearly present here. So one of the questions people ask is, first, how much energy is being put into these near inertial motions, and what are the mechanisms by which these near inertial motions in the mixed layer can get dissipated? I will skip this part in the interest of time. This is related to, perhaps I'll just tell you about the equations at the top here. I spoke about the slab model, in which you assume the mixed layer to be a very thin slab, and then you integrate the equations over depth over the thin slab, and also linearize the equations, assume small perturbations, and finally the currents in the very thin slab of ocean, which provides the first response to any atmospheric forcing, by the way. And that the dynamics of those currents is driven by the stress that acts on the surface of the ocean. All right, and to these simplified linear equations, you can write down the general solution. If you have a sudden change in the wind stress, It contains a steady state. So if you have winds all the time acting, and let's say it's steady, it would result in some currents that are generated. There is a relative direction also between these winds and the currents that are excited. We will talk about it later. But then there is also that's the particular solution. That's the first one term. And there is also a homogeneous part to these equations in the simplified model, right? And this homogeneous part is at the natural frequency or is at the local Coriolis frequency. Now, but then people realize that this homogeneous solution does not survive forever. After a point in time, you don't see these near inertial oscillations in the mixed layer. So there should be mechanisms by which these near inertial oscillation energy goes away from the mixed layer, either in the form of near inertial waves that go to the deeper parts of the ocean, or there may be other local processes that are converting this near inertial energy into some other forms. And that's again an active question. There are several mechanisms that have been identified. People study again one of these processes. Jim studies quite a bit on the interaction between these high frequency near inertial or internal waves in general with the small frequency geostrophic motions. You can have radiation of near inertial waves into the deeper ocean or nonlinear interactions. Triadic resonance is again one possible mechanism, or interaction with the turbulence that is locally present anyway because of the wind forcing that is present in the upper layer. All right. So the radiation of inertial waves into the deeper ocean is one mechanism I have spent some time studying. And there it has been recognized, this is due to one of the papers in the late 80s, that the beta effect, the fact that the Coriolis frequency changes with latitude, can have a significant influence on accelerating the rate at which the near inertial oscillations would propagate into the deeper ocean as near inertial internal waves. Okay, and the main idea there is that you had that term e power I ft. Now instead of f being a constant f naught, if you substitute that as f equals f naught plus beta y, right, and then look at it in terms of as you wait for longer and longer times after the wind stress change or the storm has passed, beta t is a wave number in the y direction that you are introducing. So naturally, because of the beta effect, you are introducing smaller and smaller length scales. And it turns out for these near inertial waves, smaller the length scale, faster they would propagate into the deeper ocean. Okay, that's just the tip of the iceberg. I don't have time to go more into this process, but then that's what the beta effect can do in accelerating the downward propagation of inertial waves. And now it's not necessarily just the beta effect that provides this additional f or the variation in f. You can have background geostrophic eddies that pass through these regions of near inertial waves, and that could provide effective changes to the background rotation that these waves experience, right? And that could also accelerate this downward propagation of inertial waves. All right. So what about is of course. I have talked like internal waves are the all important phenomena in the ocean. That is not the case. There are several other processes of importance, but particularly in the last few minutes, I would like to focus on the low frequency range in the spectra that I showed, right, of the order of 40 days or larger. Now, in this frequency range, there can be waves too. And we are going to show a really nice illustration of what are called Rossby waves that are present in satellite data. All this analysis is thanks to Nihar, who, as I said in the first slide, is a postdoc in my group. So what he has done is taken 3 decades of satellite data of the oceans, the satellites looking at how the ocean surface is moving up and down. And it is measured as what is called the sea level anomaly. Okay, and let's not even worry about how they are converted into currents. We are just looking at how the sea level anomaly, which is the deviation from its average behavior. And he has taken data over 30 years and done a frequency analysis. Now, because it's the data from satellite, you also have information on spatial variations. Unlike the mooring, which did not give you any information about lateral variations, now the satellite data gives you spatially extended information in the entire Indian Ocean. Right? That's an advantage. But the spatial resolution is still not going to resolve all the scales that are present in the flow. In this specific example, it resolves scales of the order of 25 to 50 kilometers or larger. So there is still a lot of progress being made in satellite technology to see if this resolution can be brought down. And the temporal resolution again is not as fine as what was achieved with the mooring. Here you get 1 point every day, I believe. Yeah, every day. There is one satellite pass or once every 10 days over a specific location. We also do some interpolation and numerical modeling to give a product that is with a 1-day resolution. Okay, so the temporal scales that you're resolving with these currents is of the order of 10 days or more. And then what you do is take this 30 years of data, subject it to a Fourier analysis. But then given there is also spatial information, what you do is identify some specific latitudes. In this results that I'm going to show in the next slide, it's 5 to 8 degrees north, which is in the Arabian Sea side of the Indian Ocean. Okay, maybe I can go there. Yes, so this is data that is averaged over a latitude band of 5 to 8 degrees, but the variations along the longitude has been retained. So now instead of just plotting a single one-dimensional curve with frequency as one axis, you can have frequency on one axis and a wave number in the longitudinal direction, because that variation is present, whatever scale is resolved, right? And instead of now one-dimensional plots, you have the color indicating what the power spectrum is. Am I making sense? So now, you analyze that data and see that on the frequency wave number space, this is what you get from the data. So the color is all entirely from observations or from data. Now you try and interpret. First question you ask is, hey, there is very strong signal seem to be present along a specific direction on the wave number frequency space. What can it be explained by? This is dominated by some specific wave phenomenon that is happening at this low frequency range. Okay, and this is an aspect of this plot that I very much like. This is frequency in cycles per day, but you also see the corresponding period in days that is indicated on this axis. That immediately tells you that you're talking about tens of days here in the upper part of this axis, going towards very large hundreds of days as you come down, and going towards infinitely long periods. Right? So what I plotted, or what Nihar has plotted with this blue curve, is the dispersion relation governing what are called Rossby waves. I have not had time to go into the physical background of what drives Rossby waves. Okay, beta, I'll just show you the dispersion relation and tell you what are the essential mechanisms. So this is the frequency omega of mode little n, and that's directly proportional to that coefficient beta that governs the latitudinal variation of f, right? And you have the wave number along the zonal direction x, kx, and along the meridional direction ky. And this is something related, this is the inverse of the Rossby deformation radius that Jim talked about. Okay, and I'll just point out that beta is an essential mechanism for this Rossby wave propagation. If beta is 0, if you don't account for this variation of the Coriolis parameter with latitude, then there is no omega is just going to be identically 0. So that's an essential mechanism. The physics of it we can talk about later. And interestingly, the dispersion curve seems to capture the region of significant strength in the data up to around 60 days time scales. There is still a range of smaller time scales. So this is neither high frequency. High frequency, the internal waves I was talking about is all here, a few days or lesser. And the really small frequency or slow time scales are which is captured well by Rossby wave dynamics. So what we learn from this picture is that the really small time scales, the really small frequencies, this is the really large time scales associated with corresponding wavelengths, the lateral wavelengths that you see here. You multiply these degrees by 100 to get these numbers in kilometers. -5 degrees is like 500 kilometers. Is it okay? So those scales seem to be captured well by Rossby wave dynamics. And that's something very useful to learn, saying that at very large scales and very low frequencies, the dynamics are essentially Rossby waves. But then there is also this question of, hey, what about the rest of the spectrum that we see here? That's a problem that we are still working on. There is something we have. So what he has done here is, again, this is a movie I very much like. in a specific year, 2017. Okay, and we saw that there are these intermediate time scales. There is signal at intermediate time scales. So you're looking at the flow. These are currents as obtained from satellite measurements on the ocean surface, right? And so this is essentially a zoomed in view of those really large scale movies that Jim showed. And you can also plot the same data in what is called a Helmholtz diagram, where on the x-axis you have longitude, that's a spatial coordinate, and on the y-axis is time. So you have averaged over the other coordinate, which is the latitude, right? This is averaged in this band. And as time, so you can see even the direction of wave propagation. If waves appear, you will clearly see a specific frequency or a time period that appears in the vertical direction. But the advantage of such plots is that it also tells you about the propagation of these waves in the longitude direction. And it turned out, as we looked carefully into this movie, those intermediate time period signal was associated with some couple of large anticyclonic eddies that are present in this region and their interaction with this coastline. So these are not linear, at least these are not linear Rossby waves. Clearly, the linear Rossby wave dispersion relation also did not capture that part of the intermediate time scale part of the plot. Right? And you also see that there is some instability occurring on the edge of this really large scale eddy, and that instability generates an eddy that goes around. So there is a time scale associated with it. But right now, we don't think this is actually a Rossby wave that explains that part of the spectrum. We are still spending time looking at what is the nature of the instability. Like someone asked about Kelvin-Helmholtz. There are other instability mechanisms that are possible in these systems. We are looking at what instability mechanisms may be driving this phenomenon that seems to happen, and this is not a one-off. We have seen this phenomenon happen over multiple years over this 30-year period. So it seems to be recurring. When exactly it gets initiated, what is the mechanism driving this, introducing these time scales are aspects that we are looking into right now. So to summarize, internal waves, fascinating topic for fundamental research, right? And I have focused on application to the oceans, but these are very important for the atmosphere as well. Storms that occur in the atmosphere or other forcing mechanisms when winds interact with mountains can generate these internal waves that propagate into the higher altitudes of the atmosphere. The high frequency content in a spectrum that we got from specific locations from mooring deployments highlighted that the internal gravity waves are playing a huge role in determining that part of the spectrum. Tides and winds were identified to be primary sources, and how exactly they can at least excite internal tides or near inertial oscillations is reasonably understood now. And we are actively thinking about what are the mechanisms by which they would transfer energy to other scales, both temporally and spatially, and finally result in turbulence and mixing. There are multiple candidates that have been identified for this causing dissipation, and the relative importance of each of these very much depends on the season and the location you are looking at. The low frequency range, Rossby waves seem to be governing the dynamics at large spatial scales and at these very small frequency or large time period time scales. And of course, there is, people have already shown that there is a possibility of interaction between these multiple time scales. And given the current stature, the current state of computing power, it's still very important to build semi-analytical or simplified models that look at energy exchanges between these various scales in the spectrum. That's where I'll stop. Thank you.
Okay, thanks a lot, Mani. We can have some questions.
So thank you for the nice presentation. I have a question on that near inertial wave. When you have the fresh water and the waves were damped and the ocean was not able to, or the mixler was not able to pump near inertial waves. So in the slab model, if you go into depth, like we don't have any introduction of that stratification into the mixler depth, because we take that H calculated from the mixler depth and we put into the model. that means the other way is stratification, the horizontal advection, the way the energy can be transferred. But again, in the slab model, we don't have the horizontal advection thing. Then the question now comes that how would you implement that effect of stratification into that model, simplified model? So what do you think on that?
I think there is a possibility to improve the slab model. I have not thought sufficiently about it, but right now, like you said, in the slab model, all you do is you introduce this damping parameter and choose a damping parameter that fits the data. That's what is currently done. Stratification can be one of the important mechanisms. We can talk more about how it can be incorporated into a slab model. But I haven't done it, but I think there is scope for doing this. Yeah.
I have a question. In the initial slides, you mentioned it's the deep ocean is uniformly stratified. It's actually uniform density or uniform stratification?
Uniform stratification, I mean uniform density gradient. So density is linearly changing with depth.
So the deep ocean is also stratified. There is a constant density gradient.
Yes.
So there exists internal gravity waves in the deep
Yes,
ocean.
very much. What maintains the stratification is something I don't know. But given that stratification is there in the background, it can support internal gravity waves. And that's how these internal waves are generated at ocean bathymetry. So constant n refers to constant d rho by dz.
Yeah, I have a very basic question. So, like in this stratification, you get this dispersion relation, right?
Yeah.
So, given the frequency, we were not able to find out the kx, ky. So is this because we are not looking for the particular boundary here?
Yes. So it turns out the frequency alone will not tell us what specific kx or kz will be excited. It depends on the spatial scales that are present in the ocean bathymetry. So for the problem of internal tide generation by ocean floor topography, you have to look at what spatial scales are present in the bathymetry, and that in turn will tell you what kx and kz will be excited.
Okay. And the second question is there any special space part in the ocean where we could have the internal waves, but it won't decay or it won't modify in such a way that it doesn't help in mixing throughout the depth?
So internal waves are always, depending on the frequency, they are going to be propagating away from the source in general.
Yes.
You can have very special scenarios. Since you ask about it, you can have two mountains neighboring each other, and you can have internal waves getting trapped between these mountains. And people study what are known as internal wave attractors.
Yeah.
Okay, but it's the evidence for it in the lab. You can generate an internal wave attractor. Whether such a thing really occurs in the ocean is not known at all. So it is possible energy can get concentrated in regions, but then energy cannot continuously accumulate. It will finally result in small scale turbulence and dissipation, conversion into cost mixing, and conversion into heat.
Yeah, the question why I asked this, like if there is no mixing throughout the depth, the organism which is very below to the ocean, they won't survive, right? So like, is there any space where we won't find any organism in the ocean, deep ocean?
That's first I don't know. I don't think it depends only on internal waves. Internal waves can contribute to bringing in nutrients to different depths. So in that sense, internal waves can promote organisms or biological activity, right? But internal waves is not the only way by which biological activity or transport of nutrients happen. So just because some place is devoid of internal waves, you cannot conclude that biological activity will not be there.
Okay, but largely in ocean, this is done by the internal waves, right? The gravity wave, the mixing.
Yes, but transport of nutrients is a little different from mixing.
Okay.
So you can still have mass or nutrients be transported, and that is not asking the same question as how much mixing is cost.
Thank you.
Maybe we'll have one more question and then stop.
So in the slide where you showed the wind to near inertial motions, the slab model, there the western part of the western boundary showed more intensified dissipation, right? So I can see that the year is 1982. That is the peak El Nino year. So can we generalize the figure, since it is an El Nino year, it's an anomalous, the western intensification will be anomalous. So can we generalize for all the years?
So I think similar maps have been generated for other years as well. I don't think this conclusion is based on this year alone.
Okay.
So while El Nino may change some of these magnitudes, but the general result of western intensification during winter storms still holds even during other years. But how much anomaly will be there during these El Nino years, I don't know.
So
Maybe
it does not depend very much on SST. Is that what you mean?
it does not depend very much on, well, it does depend on the mixed layer depth. So as I said, the upper layer provides the first ocean response to atmospheric forcing. It does depend. So there is scope, the possibility that some of these numbers have bigger anomalies during these years. But that's something I don't know if people have done. I do not know. But the general conclusions written here is true for every year.
Okay, thank you.
Yeah.
Okay, so we'll end with that. We have lunch arranged somewhere there. So we'll break for lunch and then we'll meet back here at 1:30. So let's thank Mani once again for the stuff.